This video will go over some of the basics of angular momentum very briefly. The objectives of the video is to introduce angular momentum as a quantity and to introduce the concept of the conservation of angular momentum as a way of solving problems. The video will also apply the concept of conservation of angular momentum to a couple of problems to show how it's applied in solving such problems. Alright, so to introduce angular momentum firstly, any rotating system requires a torque to slow it down. How difficult it is to slow down an object that's rotating is measured by its angular momentum. The angular momentum has the symbol L, and it is the product of its angular velocity omega and its rotational inertia I. The equation looks like this, where L is the angular momentum, I is the rotational inertia, which you can remember depends on the mass and the effective radius of the object, and omega is the angular speed. Angular speed is in radians per second. Rotational inertia is in kilogram meters squared, and angular momentum is in kilogram meters squared per second, which is the product of kilogram meters squared and radians per second. Radian technically doesn't have a unit because it's the ratio of two distances. The other thing to note about angular momentum is that it can have two signs, and we're going to use the convention that anti-clockwise is positive and clockwise is negative. It's interesting also to derive the equation for a point mass because its equation is going to be a little bit simpler for its angular momentum. The reason why a point mass is interesting is that we could then use that in principle to derive the angular momentum for any object, but we're going to work through the derivation for a point mass. We know we've just defined that L is equal to I times omega. So in the case of the point mass, it has some rotational inertia, and as it moves around the circle, it will sweep out an angle, and the rate of angle change divided by time change is omega. So we can write in our expressions for I and omega, because all of the mass is concentrated at a radius r for the point mass, its rotational inertia is mr squared, and we're going to multiply that by the angular velocity, omega, but we know that omega is just going to be the linear speed of the point mass divided by the radius as we defined earlier, v over r. So here's our equation for the angular momentum of an object moving in a circle of radius r, but we can cancel one of these r's to make it a bit simpler, and we get m v r. So for a point mass, the angular momentum L is just equal to the mass of the object times its linear speed as it travels around the circle times the radius of the circle. So here's a basic example of how we can apply the definition of angular momentum. So we have a flywheel, a solid disk of radius 2 meters and mass 5 kilograms, and it rotates 10 times per second. Find its angular momentum. Well, we know that L is equal to the rotational inertia times the angular speed, and we know that I for a solid disk, I is equal to a 1/2 mr squared, and the angular velocity is, we can figure out what it is from the information given. So let's find omega. omega is equal to the change in theta over the change in time. And the change in theta in this case is 10 times per second, so that's 10 times 2 pi over 1, which gives us 20 pi radians per second. I is equal to half mr squared, which is equal to 1/2 times 5, which was the mass, times 2 squared, which is equal to, what's a half times 5 times 4? 5 times 4 is 20, divided by 2 is 10 kilogram meters squared. So L, which is equal to I times omega, is just going to be 20 pi times 10, or 10 times 20 pi, which is equal to 200 pi, or 200 times pi is 628. Just make this small. Equals 628 kilogram meters squared per second. Okay, so that's how we use this equation to determine the angular momentum. Angular momentum is useful because angular momentum is conserved. If there's no external torque acting on the system, the angular momentum will remain constant. So if there's a change in the rotational inertia of the system, and there's no external torque, then the angular velocity will also have to change in order to keep angular momentum constant. Sorry, this should say momentum. Okay, so let's look at this application here. We have a skater who's spinning with her arms outstretched. So we can say Li is equal to I times omega I. And she then pulls her arms in so that Lf is equal to If times omega F. Now, what the conservation of angular momentum says is if there's no external torque, which there almost will not be in this situation because her skates in contact with the ice will have very little friction, then so if net torque equals 0, then Li is equal to Lf. So in other words, we can say I times omega I will be equal to If times omega F. So I'm just going to rewrite this so that we can make a quick statement about this. So take this, we'll put it down here. So if we rearrange this for omega F, we get omega F is equal to I initial over I final times omega initial. So in the case of the skater here, when she pulls her arms in, her rotational inertia decreases. So If is smaller than II, which makes II divided by If a number bigger than 1. When we multiply that by the initial velocity, angular velocity, we'll see that the final angular velocity will be bigger than the initial angular velocity. So this is a typical example where the conservation of angular momentum can help you deduce interesting information about the system. Okay. So to show how we can apply this in an explanation style question, we'll go through and explain why the skater's angular velocity increases as she pulls her arms in. So the first point to make here is that as she pulls her arms in, her effective radius decreases. And that will lead to her rotational inertia decreasing. So thus, her rotational inertia decreases as I is equal to m times R effective squared. As there are no outside torques, angular momentum is conserved. So if her rotational inertia decreases, her angular velocity must increase. As L is equal to I omega. So basically, if I goes down, omega must go up so that L doesn't change. Okay, so this would be the ways that you would go through the steps. So first explain why her rotational inertia decreases. Then explain that their angular momentum will remain constant. And then explain that if her rotational inertia decreases and angular momentum is to remain constant, then her angular velocity must increase. Okay, so then we'll look at an example using some numbers here. So we're told here that the skater's initial rotational inertia is 7.5 kilogram meters squared. So we can say I initial is 7.50 kilogram meters squared. And we're also given that omega I is equal to 10.0 radians per second. She pulls her arms in, reducing her rotational inertia to 2.5 kilogram meters squared. What will be her new angular velocity? So we can say IF is equal to 2.50 kilogram meters squared. Omega F is what we're trying to find. Okay, then we'll say, assuming no external torques, so then we've kind of answered the second part of the question. Li equals Lf. So II times omega I must be equal to IF times omega F. And now we know everything except omega F here. So we'll just rearrange it for omega F first. Omega F is equal to II over IF times omega I, which is equal to II was 7.5 over 2.5 times omega I, which is just equal to 7.5 divided by 2.5 is 3 times, in fact I was putting numbers in here, I might as well put in 10 here, which is equal to 30 radians per second. So we can also see here, having solved this problem now, that because the rotational inertia decreased by a factor of 3, the angular velocity must have increased by a factor of 3 in order to keep the angular momentum constant. Okay. A third type of example, where we would apply the conservation of angular momentum, is this type of example. So here we have a disk rotating. We call that disk 1, or a turntable. and we are dropping a second disk on top. And when they collide, when the top disk lands on the bottom one, the top disk will start spinning, and this will also slow down the spinning of the bottom disk. However, there are no external torques acting on this system, so the angular momentum should remain constant. So we'll have a look here. So we've got the horizontal turntable with rotational inertia I1 equals 0.030 kilogram meter squared. So we can find before L is equal to I1 omega 1, which is equal to 0.03 times 6, which is 0.18 kilogram meters squared per second. Okay, so that's the angular momentum before. And then we can say, as there are no outside torques, Li is equal to Lf. But afterwards, the rotational inertia has increased because we're now rotating 2 disks instead of 1. So therefore the angular momentum, because the angular momentum must remain the same, the angular velocity must decrease. Okay, so what are we told about the final situation? Lf is equal to I1 plus I2 times omega f, because now we have not just one disk, but we have 2 disks spinning, and we're going to add the 2 individual rotational inertias to find the total. So and what we're trying to find is this I2 here. We know omega f, we know Lf, and we know I1. So let's do that. Let's rearrange this for I2. So we get Lf over omega f is equal to I1 plus I2. So I2 must be equal to Lf over omega f minus I1. And we know what all of these 3 things are, so we can figure that out. I2 is equal to Lf, this is equal to Li, so which is equal to 0.18. And so let's now solve this. We have 0.18 over 4 minus I1, and I1 was 0.03, which is equal to 0.18 divided by 4 minus 0.03, which is 0.015. kilogram meters squared. Okay, so here we can see that, just to go back over what we did, we worked out what the total angular momentum was in the system by figuring out how much there was before the collision. Then we noted that the total initial must be equal to the total final. Then we wrote an expression for the final momentum, final angular momentum, which included the quantity that we wanted to figure out. This is basically just the total rotational inertia times the final angular velocity. And then we rearranged that for the quantity that we wanted to find out. Okay. There are several other examples that work in a very similar way to the ones that we've looked at. So here we have an example of a diver in the top left here. The diver has no external torques acting on her because the only force acting on her is acting through her center of mass. And so because that's 0 distance away from her center of mass, that will not produce a torque on her. However, when she jumps, she applies a torque to herself, which causes her to spin. As she tucks, her rotational inertia decreases. So here we have let's go back here. So at this position, I is small and omega is big. And then what she does is she comes out of the tuck when she's about to hit the water to slow down her spinning and give herself more control. So at this position, I is big and omega is small. And angular momentum is conserved throughout because there are no external torques on the system. Another common example is this example of a person sitting on a chair, rotating with some initial angular velocity and holding a lot of weight away from his body. And as he spins, he then pulls his arms in so that his mass is concentrated closer to his axis of rotation. So I decreases and Li equals Lf, so omega must increase. So what happens is he speeds right up and his rotation rate gets much higher. His angular velocity gets much higher. Another kind of cool application of this is inside satellites. This is the International Space Station, I think. They have little gyroscopes or little discs that can rotate. They're attached to electric motors. And if these things are all sitting stationary inside this, this will be tucked inside the space station somewhere. What they can do is they can make these wheels spin, and when they do that, the space station will start to rotate in the opposite direction to keep angular momentum constant, and that allows them to redirect or realign the space station. For example, if they want to make all the solar panels face the sun, or if they need to send a transmission down to a particular point on Earth, by having 3 of these little spinning disks, they can rotate the space station so that it points at any angle. So just to summarize here, angular momentum measures how hard it is to stop something that's spinning, and it depends on 2 things. It depends on the rotational inertia I of the object and the angular velocity omega of the object. Angular momentum is conserved as long as there's no external torque acting on the system, or if the torque is negligible. So if you have a system where there's an axle and something's spinning, and they say that it's a low friction axle in the question, then you can say, assuming that external torques are negligible, angular momentum will be conserved. And you often have to make that assumption to approximate an answer. This means that for a rotating system, the initial angular momentum is equal to the final angular momentum, or, in other words, the initial rotational inertia times the initial angular velocity must be equal to the final. So this means that if the rotational inertia of a system changes, then its angular velocity will always change. If we rearrange the equation, this is a useful form to know. If we want to figure out what the final angular velocity of an object will be, then we can just take the initial rotational inertia divided by the final rotational inertia and multiply it by the initial angular speed, and that will give us our new angular speed. So in other words, if the rotational inertia decreases, then that'll make this number here bigger than 1, which means that omega f will be bigger than omega I. If, on the other hand, the rotational inertia increases, then the initial will be smaller than the final, and omega f will end up being smaller than the initial.